Okay, hi everyone. So for this Synvascular tutorial, we'll be introducing reduced order modeling methodologies, specifically 1D and 0D models in Synvascular. We'll first focus on a background and theory of 1D and 0D models, and then we'll follow up with a live demo of the 0D pipeline inside the Synvascular GUI. So the 1D pipeline was already covered in a previous tutorial, so if you haven't seen that yet, go ahead and check that out on the YouTube page. And then, of course, if you have any questions, please hold them until the end of the presentation for our Q&A session. So let's begin. The two reduced order modeling methodologies implemented in Synvascular are 1D and 0D models. But what exactly are 1D and 0D models? So in previous tutorials, you learned how to create 3D models in Synvascular. And like the name suggests, 3D models are three-dimensional models in space, and they give us information on the spatial distributions of velocity and pressure. And then 1D models, on the other hand, are just one-dimensional models in space. And the only spatial dimension that they have is the axial dimension along each vessel branch. And as such, 1D models can only provide us with spatial distribution of the flow rate and pressure along the axial dimension of these vessels. And finally, we also have 0D models, which provide no spatial information whatsoever, hence the name 0D or zero dimensional. And these models, they're purely time dependent, but they provide us with both global hemodynamic quantities as well, primarily flow rate and pressure. So this begs the question, if 1D and 0D models provide us with less information than 3D models, then why should we even use these reduced order models in the first place? Well, the primary advantage of these lower fidelity models is that they're significantly cheaper to simulate than 3D models. And they're so cheap that we can often simulate them on a laptop with just a single processor, as compared to 3D models, which often require many hours and many computational resources, such as like multiple processors or a supercomputer to simulate. So now let's quickly discuss the 1D and 0D models in Synvascular. So how are these reduced order models generated in Synvascular? So first we begin with a 3D model, and then we generate the center lines corresponding to this 3D model. We'll extract, we'll use the information on the center line and extract the relevant geometric and material properties, such as the radius and lengths at each cross-section, and the relevant material properties, such as viscosity, to create our 1D and 0D models. So then we can simulate these 1D and 0D models using their respective 1D and 0D solvers, which you can find on the posted GitHub repositories here. And these solvers are also integrated into Synvascular already. And in the next section, I'll briefly cover the relevant theory governing these reduced order models, but you can also find more detailed information on the linked documentation found on this slide. So now let's quickly talk about the theory of 1D models. So as mentioned earlier, 1D models have only a single spatial dimension, the axial dimension along each vessel branch. And these models are of course time dependent. And again, 1D models can simulate bulk hemodynamic quantities such as flow rates and pressure. But they also can simulate wall shear stress and cross-sectional area. And for each of these quantities, we simulate their spatial distribution along the axial dimension along each vessel branch. And then last thing, it's important to note that at the junctions between different vessel branches, we assume that pressure is constant and that mass is conserved, which simply means that the inflow going into the junction is equal to the outflow. So now the 3D models are governed by the 3D Navier-Stokes equations, right? When we integrate these equations over the cross-section of each vessel, we obtain the 1D equations, which are the governing equations shown here. And these equations model the interaction between the flow rate, the pressure, cross-sectional area, and they can also allow us to model a deformable wall behavior. So with two governing equations, but three unknowns, again, flow rate, pressure, and cross-sectional area, then we need one more equation to close the system. And here we use the Olesen constitutive law to model the relationship between pressure and cross-sectional area. And if we want to model rigid wall behavior, rather than deformable wall, we can just set the Young's modulus in the constitutive law to be arbitrarily high to represent like a stiff system. And in order to solve these equations, we use a stabilized space-time discontinuous Galerkian finite element method. And as mentioned earlier, we assume that pressure is constant at the junctions and that mass is conserved there. So that briefly covers our background on the 1D models. Now let's quickly talk about the theory and background of 0D models. So 0D models are lightweight methods to simulate bulk hemodynamic quantities in the cardiovascular system. And unlike 3D and 1D models, 0D models are purely time dependent. They can only simulate global flow rate and pressure quantities, but while 0D models don't have any spatial information, they are highly modular and compartmentalized, which means that different regions of the 0D model represent the hemodynamics in different parts of the cardiovascular anatomy being modeled. And furthermore, 0D models are analogous to electrical circuits. So the flow rate simulated by 0D models represent electrical current, while the pressure represents voltage. And there are three primary building blocks for 0D models. Those are resistors, capacitors, and inductors. And so resistors represent or capture the viscous effects of the blood flow, while capacitors capture the compliance and distensibility of the vessel wall, and inductors capture the inertia of the blood flow. And so different combinations of these building blocks, as well as other blocks like flow sources or pressure sources, can be combined to reflect the hemodynamics and physiology of different cardiovascular anatomies. And in order to compute the resistance, capacitance, and inductance for each blood vessel being modeled, we use the geometric and material properties from the 3D model and the centerline. And here for the resistance, which is capital R, and we can see it's a function of mu, the viscosity, and then the length of the vessel L and the radius of the cross-section, little r. And then capacitance, capital C. You can see it's similarly a function of radius and length as well. It's also a function of the Young's modulus E of the vessel wall, as well as H, the thickness of the wall. And then the capital L represents the inductance here. And that's also a function of the length and radius, but also the density of the blood. Rho, yeah. And so as we just mentioned, the 0D models, they're highly modular, and they can be constructed by these resistors, capacitors, and inductors, and like other flow and pressure sources as well. And when we assemble these different building blocks together and their respective local governing equations, we ultimately arrive at a global system of governing equations, specifically a differential algebraic equation as shown here. And so the values, the coefficients for this differential algebraic equation are dependent on the building blocks that we choose, that we use to construct our 0D model. And then in Synvascular, we solve this global equation using a generalized alpha time stepping method to simulate the flow rate and the pressure, as well as other hemodynamic quantities of interest, such as volume in chamber models or other things like that. So in the 0D model, in the 0D solver, we have the following 0D options to model blood vessels. So we can use a basic resistor, which again just captures the viscous effects of the blood flow. But if we add a capacitor to this resistor, then we get a combined resistor capacitor element that captures both the viscous effect as well as the compliance of the vessel wall. We can also use an inductor in conjunction with our resistor as well to capture the inertia of the blood flow as well. And if we combine all three elements, then we can create a resistor, capacitor, inductor element that captures all three effects. We also have a stenosis element that enables us to capture the energy dissipation from the expansion and flow separation induced by stenosis. And in the future, we're also working to create a combo type of 0D block that enables us to use a stenosis, resistor, capacitor, inductor, as well as other future 0D elements that we might be interested in to add more complexity to our 0D model. And furthermore, similar to 1D models, we also assume that pressure for now is constant at the junctions and that mass is conserved there. And in the future, we're also looking to implementing more complex junction models, including ones that can capture the pressure loss induced by the branching. So lastly, our 0D models, we represent the downstream vasculature using various boundary conditions. So both the 0D and 1D models, as well as 3D models, we have these resistance boundary conditions, but we also have RCR. We also have more complex ones like RCR and coronary, which again just capture the resistance and distensibility of downstream vessels. But the coronary boundary condition also captures the interaction between the heart and the coronary vessels as well. And so that concludes our brief overview of the theory and background for the 0D models in Synvascular. And so now we want to proceed by giving you a peek at the performance of 1D and 0D models when we compare them to 3D models. And so the results that I'm about to show right now, they're still preliminary. And so we're still working on this, and there still might be more things we need to add to these results in the future. So for our comparison here, we're using the data from the vascular model repository, which is just a collection of fully simulated 3D vascular models consisting of various anatomies such as aortas, pulmonary and coronary systems. And here in this slide, we use a bar plot to demonstrate the performance of 0D models versus 3D models for the models I just showed in the vascular model repository. And so each column in the x-axis of our bar graph corresponds to a different model, and the y-axis is the pressure error averaged across all the inlet and outlet caps for each model. And observe that for most models in the repository, the average pressure error at the caps is less than 10%, which demonstrates that, on average, our 0D models are capable of accurately simulating the hemodynamics. And also recall that 0D models are significantly cheaper to simulate than 3D models as well. So if your goal is to obtain global pressure quantities, then a 0D model may help you obtain those results very cheaply and very efficiently. But to observe that, we have some 0D models where we have relatively large pressure errors. Here, I mean relatively large by like greater than 10%. And here, I circled those here in the top right for the two pulmonary models shown in the top right corner. And so we're still digging into reasons why our 0D models do not perform that well here. But one theory as to why this is happening is that, there are these large area changes that happen across a junction in a pulmonary model. And right now, our 0D models currently don't take that effect into account. So these large area changes in the junction, they can lead to drastic pressure changes in those areas. And so future work would entail creating a new junction block that can model this type of pressure loss in our junction. So here we show a similar comparison between the 1D and 3D models. So like the 0D models, the 1D models perform very well in general, and we generally have pressure errors that are less than 10%. But there is one model here that yields a larger than 10% error in pressure. And that model is a severely stenosis aorta, as shown on the right. And so it's important to note that earlier, like I mentioned, our 0D models had this extra stenosis element that enables us to capture the energy dissipation caused by the stenosis, right? Caused by the severe area change. But our 1D model doesn't have such a stenosis model yet. So we're working to implement this in Synvascular, and we think that this addition will greatly improve the results and allow our 1D model to model vascular anatomies with this type of severe pathology in the future. And so that concludes our quick comparison. Oh, and so that concludes our comparison of 1D, 0D, and 3D model. And in general, as we've seen from our preliminary results, the 1D and 0D models are capable of accurately simulating flow rates and pressures, and they're also significantly cheaper to run than 3D models. So there's that advantage as well. And so thanks for listening. If you have any questions, please feel free to ask. Otherwise, Martin will take over and demonstrate the 0D modeling pipeline in the Synvascular GUI.